Hello everyone, welcome to another episode of Linear Algebra. Till now, we have completed 5 episodes of Linear Algebra. In that, we have covered different topics like intuition of how we imagine linear combinations. We have seen multiple elimination methods, Gauss-Jordan elimination, Gaussian elimination, and different sort of things. And we have talked about inverses, how do we even imagine inverses, transposes, symmetric matrices like this. We have covered most of the part like vector spaces, column vectors and all. Now, in this video, we are going to talk about one of the most important topics of linear algebra, which is eigenvectors and eigenvalues. And this is the introduction or video of this entire eigenvectors and eigenvalue. And I wanted to make this intro or this entire session, this episode 6, a little bit different because till now we have been talking about theory stuff, right? We have been talking about like how do we imagine it? What is the mathematical representation of every other concept that we have learned till now? I wanted to make this episode a bit different, right? I wanted to add practicality as well. I have talked about the implementation of eigenvectors and eigenvalues. Where do we actually use them? And I have talked about a concept called as PCA, Principal Component Analysis, which is one of the most important and most powerful topic in machine learning. So, we will try to complete linear algebra in this lecture, and there will be one more lecture. After that, we'll directly go to calculus and probability. And after completing this math for AI, we will move to machine learning, which will be complete code and practical implementation. We'll not talk more math now because I want to cover more topics in a short span of time. So this is it. I hope you will enjoy the most important and most beautiful concept of mathematics in linear algebra, which is eigenvalues and eigenvectors. So with that being said, go ahead and watch the entire lecture. And if you have any doubts, please do comment. I'll more than happy to answer those. So see you in the lecture. In the previous lecture, we have studied different concepts of linear algebra, like we have seen what is the meaning of vector, how do we do Gaussian elimination, Gauss-Jordan elimination, how to find inverses, how to find transpose, symmetric matrices, and what is the actual meaning of inverses and all. Now, we are going to talk about a topic, and the topic name is eigenvectors and eigenvalues. Okay, so before we start the topic, there are some prerequisites that we have to know at any cost. Without them, I don't think so we'll have a definite image of what is the meaning of a eigenvalue and a eigenvector. Because in school, we might have studied like how to calculate them and all, but somewhere deep down, we haven't figured out what is the meaning of exact eigenvector. When I say eigenvector, how do we imagine that? What is the meaning of that? So we are going to cover this topic in detail. We'll cover the math as well, along with the intuition, visualization, and complete understanding of eigenvectors and eigenvalues in detail. So the prerequisites are, the first and foremost thing is we should start with linear algebra. When I say linear algebra, the thing is the first fundamental place where linear algebra begins is vectors, right? And as I said before that, depending on subject, depending on which subject you are studying, the definition of vectors changes time to time. And it's not a problem if you see as such, right? For a physics student, the vector might be a fundamental unit which has some direction and some value associated with it. Similarly, for computer science student, a vector is basically a single dimensional, or you can say a vertical numbers which has like vertical list of numbers. That's it. This is how we represent vector, like 1 2 3 can be a vector, 0 1 can be a vector, or else pi comma e can be a vector, like this. For computer science student, this is the definition of vector, and they don't have to see like what is the meaning of this and what do we do with it. They don't care. What they care about is that, like, how can I use this to perform my computational problems, right? Computations and all, like, because just imagine, I will give you an example to understand that. Imagine that I have given you a list of prices of houses. They are 10 houses, and each element, or you can say each value, represent a house price. Let's say 10 crore, 20 crore, 30 crore, 40 crore, 1 crore, something like that. So this is a vector in itself, and what it represents here, it represents list of houses. Similarly, here this can be just random numbers, and this can be some random symbols. It doesn't matter. What matters is what is the problem statement, and how they are going to use this vectors to proceed with their computation, proceed with their calculation. That's it. This is what matters to computer science student. They don't have to see what is the unit, what is the direction and all. It doesn't matter to them. Now, when it comes to math, we are studying pure mathematics, right? So pure mathematics, I would say, try this pure mathematics in linear algebra tries to combine this and this together. So what we will do is that we write vectors in this form. When I'm writing vector v, let's say I'm writing 2 comma 1. What I mean by this vector is that I have a two-dimensional grid or two-dimensional space. This is my x-axis, this is my y-axis. In that, I have to travel 2 units in x-axis first. So 1, 2, 2 units in x-axis and 1 unit in y-axis. Whatever the intersection point I'm getting, right? This is the intersection point. So from origin, if I draw a straight line, then this is my vector v. This is how we do. If you see, we have a direction and we are representing this in a form of numbers as well. So somewhere deep down, we are trying to combine both concepts, right? And let me remember, like, tell you this, that in math there are some properties, and because of this properties, it differentiate mathematics vector from a physics vector. And what are these properties? If you remember that, in physics, vectors can be anywhere. It can start from origin, it can go like this, it can be like this, it can be anywhere. But in mathematics, we introduce some properties which a vector has to follow. If it is a linear algebraic vector, then it has to follow these properties. What are these properties? The properties of a given vector in a given space is that vector in a given space is that, let's say I have two vectors v and w. So if I have two vectors, then the first property says that I should be able to add these two vectors, and the resultant vector should be in the given space. For example, if the vector is in R2 dimension, then the addition of these two vectors will also be in R2 dimension, right? If I'm multiplying given vectors with a scalar, let's say c1v plus c2v, or without even adding, let's say I'm just multiplying c1v or c2v. Even though I'm multiplying the given vector with a scalar, with a number, right? I'm scaling the vector. Either I can make it 2x, 3x, or half, it doesn't matter. But the resultant should lie in the given space. And because of these two rules, the linear algebraic vector has to start from origin. It has to start from origin. What I mean is that if I take this vector from physics perspective, this is a perfect vector. It has some direction, it has some value, perfect. But when it comes to math, it is not a vector. It is just a arrow, you can say, or like shape in a two-dimensional space. But it is not a vector. Why? Because vectors in linear algebra has to start with origin. If it is not starting from origin, then it is not, it is okay. Okay, it is not a, 1 second, let me optimize this thing and layout as well. So it is not a part of the given vector space. Okay, so this is what I'm trying to tell. Now, I hope you have understood the properties, what are these properties and all, and you have understood the first and foremost topic, which is a prerequisite for understanding eigenvectors. Now, the next topic is linear combinations. So you might have remembered that we used to solve the given set of equations through row picture, column picture, and finally we came to matrix elimination, and we did so many things to find out the solution. Similarly, the definition of linear combination is that, let me write it. Linear combination is, to tell you the definition, we need to take two vectors. Let's say I have vector v and vector w in a two-dimensional plane, because two dimension is easy to understand. Okay, x and y. So let's say that I have a vector v and vector w, and what I'm doing is that linear combination, trying to add them. Okay, so you're trying to add this vector with some like constants. Let's say c1, I'm trying to scale it and add it, right? C1 plus v, c2 plus w, right? Whatever the resultant I will get, right, that will be a part of the linear combination. That is a part of linear combination, right? R. Now suppose that here c1 and c2 belongs to real numbers. It means that it can range from minus infinity to plus infinity. Now if you do that, let's say I'm taking two vectors, and first of all I'm calculating with its own, like I'm not adding c1 c2. Let's say c1 and c2 is 1. Okay, now if I add v plus w, then I will get answer sum r. Now just imagine that I have updated c1 to 2 and c2 to 1. Now what happens is that 2v plus w, this will give me some other r dash. So here whatever the answers I'm getting while adding them, right? So all the combinations which are possible by just changing the scalar values of the given vectors, okay, by just changing the multiplier, whatever values I'm getting, all these results which I'm getting is known as the linear combination. This is a linear combination, r dash is a linear combination, and whatever the values I get, right, are linear combinations. And let me tell you this, if you are moving from minus infinity to plus infinity, then your r will rotate. Let's say if okay, let me draw it here for better visualization. I'm gonna take a bit of board here, so do not mind, because these are really, really important to understand. Okay, now let's say this is my r. Now I have increased the value of v. So what happens is that my r will be inclined towards v. If I increase the value of w, then it will incline towards w. Now whatever the answers I'm getting, these are known as linear combinations. Now all the linear combinations, if I'm moving from minus infinity to plus infinity, then this r will rotate the entire two-dimensional plane. And what are the answers I get, right? All the combined linear transformations, we call them as span of v and w. This is the definition of span. I hope you have understood what is the meaning of linear transformation. Basically, you're adding two vectors, and the answer you get, it is a part of linear combination. It is the answer. Now, like through this concept only, we solve set of equations. For example, let's say I have a equation 2x plus y is equals to 4, and uh, like 4x plus 2y is equals to 1. Now what we are doing is that we have a matrix 2 1 and 4 2. Okay, uh, and multiplying with xy, it is giving me 4 1. What is the meaning of this? If you see here, this is my v vector, this is my w vector, this is c1, this is c2, and what I'm trying to do is that I'm trying to find the perfect values of c1 and c2 in such a way that I want r as my resultant. So here, if this is my v vector, this is, I'm just drawing randomly, this is my w vector, then I'm trying to change the vector, stretch or compress in such a way that I want this particular r. I want this r, right? This is my r. I'm trying to get the r by just changing the, manipulating the values of v and w. right? And how I'm manipulating by C1 and C2, basically X and Y. I'm putting different values of X and Y, and I'm checking whether I'm getting R or not. If I'm getting R, then this values of X and Y are valid. If I'm getting some other thing, then they are not valid. This is how we think when we try to get the answers of linear equations. Now let me show you as well. Like I have this thing here. First of all, see, I have two vectors. I have this one vector. Let's say this is my vector u, this is my vector v. Now let me zoom it and scroll down a bit. Now here you can see I have c1 c2 values. Basically I'm like manipulating the length of the vector. C1 manipulates the length of u, and C2 manipulates the length of V. Now you can see that this is the resultant vector. The red line you are seeing is the resultant vector. Now if I increase it, you can see that the resultant vector is going up. Like it is going all the way up. It is moving in anti-clockwise direction, right? And if I increase the value of C1, you can see it will bend towards U, right? If I decrease it, it will go away. If I increase, it will like come like this. So I hope you have understood. You can see that the R is traveling entire given space. The reason why it is getting stuck here and here is because it is moving from -10 to 10 only. If it's moved from the entire given space, then the R will cover the entire two-dimensional space. So I hope you have understood what is the meaning of a transformation, and this is how a transformation looks like. Okay, and whatever the values I'm getting, right, all the combinations of R, you can see this is some R, this is some R, this is some R, like this, different resultants we are getting. This is how a linear transformation looks like. I hope you have understood. This is the, sorry, not linear transformation, linear combination, my bad, right? This is how a linear combination looks like. You are adding two vectors, getting resultant, and then you are again changing one of the lengths of the given vector by making them scaled or making them smaller, right? And whatever the answer you're getting, you're just noting it down, right? So this is how we we describe the meaning of linear combination. Okay, now after linear combination, the most important topic to understand eigenvalues is linear transformations. Okay, and linear transformations is the concept I think really important, and this concept opens up your eyes. You have to understand this concept to understand entire linear algebra. Okay, so as I said you that part the fundamental part of linear algebra are vectors. Okay, so we have vectors. Let's say I have, and before going to that, let me tell you one concept in linear combination, which is we know that when we are adding two vectors, I'm getting some resultant, and combination of all these resultants is known as span of the given vectors. Okay, now there is concept something called as unit vector. Unit vector are really important, and unit vector is the foundation stone to understand linear transformations. Okay, so unit vectors are nothing but from origin if I move one unit, and from origin if I move one unit, right? I describe this as I cap and j cap. Whatever the vector I get, this will be also a unit vector v, and unit vector v will have one of I, one of j. Okay, this is known as unit vector. So the definition of unit vector in normal two-dimensional space is a vector which is having one unit in x, and one unit in y. I hope you are taking notes because this is the most important topic in linear algebra. If I take 3D, then I will have three dimensions. It means that a vector having one unit in x, which is known as I cap, one unit in y, j cap, and 1 unit in z, k cap. So these are known as unit vectors. Now, if you are clear with unit vectors, then and only we can go to linear transformations, because without having what is the meaning of unit vector, you will not understand the linear transformations. So let me go to, I hope you are very, okay. So I hope you are very much clear about like what is linear combination and what is a span and what is a vector, unit vector. Now let's move towards another topic. And before that, let me put this in standby mode. Okay, let's go to the most important topic, which is linear transformations. Now imagine that I have a function. I have a function. Before that, before understanding linear transformation, you need to understand what is a transformation. Transformation is that, let's say I have a space. I'm taking two-dimensional space because it is easy to understand for humans, for us. So I have taken a uh, normal space, right? Two-dimensional space. Now you can see in this space everything is normal, right? Everything is standard, like whatever we imagine, right? Generally it is there already. Now if I take a unit vector will be here, and my j would be here. Okay, got it. Now, oh god, seriously, this is, I think this will not go good. Okay, anyways, so I have taken I and j. Now imagine that I have a vector, and this vector can be anything. This vector can be anything. I have taken a vector, and what I did with this vector is that I have taken a two-dimensional vector. I have put this vector in a function, and this function has returned me some output. And because of this function, the overall space, the output which I get, right, has been transformed. Has been transformed. This is the meaning of a transformation. What you're doing is that you have a function and you have a set of vectors. What you're doing is you're taking this set of vectors, putting it inside your function, and because of this function, your entire two-dimensional space is transforming. It means that it might get stretched up, it might get let's say uh, compressed, it might stretch, it might compress space, like you are altering the original two-dimensional space. This thing is known as a transformation. Okay, now just imagine, I'll tell you one example. Let's say here I have assumed that this is my standard units, and because like I have imagined that 1 unit in x is equals to my I cap and 1 unit in y is equals to my j cap, because of this assumption I got my standard two-dimensional plane. Now imagine that I have assumed that my 1 unit will be 1 by 3 and 1 unit in y would be 2. Now just imagine what will happen to space. It means that your entire space, the x directional space has been compressed and y direction has been like expanded. Okay, so here the 1 unit will be now 1 by 3. So here 1 unit of x in this transformed space would be 1 by 3, and 1 unit of y here in this space would be your 2. It means that this is my I cap and j cap. If I change the definition of I cap and j cap, then whatever the resultant space I get, right, that space is my transformed space. Okay, let me show you a visual representation, and before I go into the visual representation, there are some constraints, right? There are some constraints which you have to follow, right? We are studying linear algebra, right? In linear algebra we talk everything about linearity. Just imagine that you have a function, you have some function, and because of this function the space is getting squeezed. right? You are getting curves, then it is not a linear transformation. The space either should get stretched, rotate, or compress. And whatever the lines you have, right? If I draw lines in this space, the line should not intersect with one another, and it should not create any sort of curves in the given space. If it is following that, then it is a linear transformation. For example, my function can never be x square plus y plus z. It can never be this. Why? Because it has a polynomial 2. It has a square root, and because of the square root, because of square, what happens is that the two-dimensional space will get curved, and we don't want curved spaces. We are talking about linear spaces. I hope you have understood. So this is one constraint. Our functions should follow a linear format, right? No curve should be present. That is first rule, and there are some other rules. But um, let me tell you that let me show you one example here. So here you can see I have some space, and this is my standard space, and this is my stretched space. Now you might ask, like, Jabir, what is it, like how you are calculating it and all? Just imagine that here I have described a function. I'm writing function here. Just imagine that I want my space f of x is equals to um, f of x is equals to 2x comma wait, this is a two-dimensional vector, right? So here I will have x comma y. If it is a one dimension, I will have x. If it is two dimension, I will have x comma y. Now just imagine that I'm increasing, I'm like taking my vector and transforming the vector in this format. Let's say 2x plus y comma y, or as y plus x. Just imagine, like, I'm doing this transformation. Now what is my unit vectors? 1 comma 1, right? I comma I. Now if I multiply this with this, then what will happen is that I will get the output as uh, right, just multiply 2x plus y and y plus x multiplied by 1 comma 1. What will happen is that you will get this vectors 1 comma 1. 2x plus y is one vector, and y plus x. I hope I'm writing it right. Yep. So this is what I get, right? Let me tell you, like, let me erase it, like, to explain you this. To explain you this. Okay. In a given standard space, let me show you. In a given standard space, if my 1 comma 0, 1 comma 0 and 0 comma 1, it means that the x component here is only I, y component is only j. Then my space will remain the same, right? Now if I increase the given space by here, if you take, let me put it here, if I'm taking 1 comma 1, then what will happen is that my space will get expanded by 2 plus 1 and 1 plus 1. It means that you're increasing the x space by 3 and y space by 2. So here what I will do is that I will take the vector, x will be 3 now and y would be 2. So you can see that the space has been increased. Okay, so you can see this is 1 unit in normal scale, and this is 1 unit in our given space. Okay, and this represents I cap, this represents j cap. I hope you are clear. Are you clear till now? You can see that the x from the origin is 3, and the I from the origin is 3, and the y from the origin is 2. Are you clear? So here what I'm doing is, because of this function, a transformation is happening. Just give me a thumbs up if you're clear. Okay. Okay, so this is how the linear transformation works. And there is something which I'm missing. I can't recall exactly. I'll tell you. If I remember on the way, I'll tell you. But this is how we are changing the space. Like here, 1 unit is becoming 3 and 1 unit is becoming 2. I'll show you some other examples as well. If I diminish the space, let's say my space is 3 comma 2. Let's see what happens. You can see that my x cap is somewhere here, and this is my y cap. What happened here is that my I cap is a vector, right? And that vector is equals to, it has become V, and it is having, what did I do? What did I did here? 3 comma 2. So I did 3 comma 2. It means that I have given 3 unit in x and 2 unit in y. I have taken this as my I cap. So it can be possible, like if your I itself is a vector, then the space will get stretched something like this. So I'm like forgetting one concept. I don't know exactly what it is, but I'll tell you. But I hope you guys have understood what is the meaning of a linear transformation. Now, this is one constraint, that you cannot have equation which has higher power. Now, the second thing is that you cannot have a function which has some constants. See, you cannot have constants because uh, it violates this rule. Which rule? This rule, multiplication rules of vectors, right? If let's say I'm taking a vector f of 1, and let's say c is 5, so I'll get 5 as output. If I'm putting 2, then again I'll get the same answer. What it is representing, it is not representing a vector, it is just representing some random value on the given dimension. So you cannot have constants. That is one thing. And the third thing is that you cannot add. Let's say you have x plus 1 comma y plus 1. If you are in 2 dimension, then you cannot add. Why? Because when you add, what you're doing is that you are changing the axis like this. This is my original axis and this is my new axis, and the axis will be 1 comma 1. And if I multiply this given equation, this given vector with 0, then I should get 0 from math, but I'll remain at 1 comma 1. So that is why you cannot add. You cannot change the origin. That is the main concept. And third is fourth rule is that you should not have modulus. You know what happens because of modulus? Let's say I have taken f of 5. I'll get 5 as output. If I get minus 5, then I'll get plus 5 as output. So what happens is that if you try to, let's say if it is a 2-dimensional vector, and if you try to draw, then it will be something like this, right? And they will never hit origin. Sometimes if you take 0, then it might hit origin, but if it is a non-zero, if you are putting non-zero value, then it will never hit origin. That is the problem with it, right? And it doesn't have a reflection as well, right? A vector should go along its direction, but here what happens is that it reflects back. It will not have any mirror images associated with it. That is why you cannot take a polynomial higher than degree 1. First rule. Second is that you cannot take a constant. Third is you cannot change the origin. Fourth is you are not allowed to take modulus because it violates the addition property. Okay, for example, if I'm adding f of 5 plus f of minus 5, it will give me 10. But if let's say it is a normal function, f of x is equals to x, then it should give me 0 according to the addition property of the first rule, right? Because for this first rule, where is the rule? Because of this first rule, I should end up at origin, but I will never end up at origin. It is breaking the rule. That is why you cannot use modulus as in linear transformation. Okay, so I hope you have understood the meaning of linear transformation and everything. Let me go back. So we have covered linear transformation and all. Now let me tell you a concept which bends your mind. Okay, the concept is that I'm so fed up with this now. The concept is uh, matrix multiplication. Oh God, Jabir, why are you telling this concept again and again, again and again? So let me tell you one thing. I'm writing a matrix. Let's say A is equals to 1, 2, and 3, 4. What is the meaning of this? What is this? It is a matrix. What is the definition of a matrix? The main important thing. In schools, we have learned that a matrix is basically unit data information stored in rows and columns. No, it is not. A matrix is, let me write it, a matrix is a linear transformation, right? What it is a linear transformation. This is I cap, this is j cap. It is telling that you should bend the space with a vector v, which is having one x unit plus two y unit, and the vector j will be some vector w, which is having three x unit and two y unit. This is the definition. So if someone asks you from now on what is a matrix, tell them it is a linear transformation, right? It is a linear transformation. That's it, right? It represents a linear transformation. And what happens in vector multiplication, right? Sorry, matrix multiplication is that I'm taking a matrix, another matrix, square matrix only, 2, 1, 4, 3. Okay, I have taken reverse. Now, if I multiply, if like this represents space 1, this represents space 2, and this two spaces belongs to two-dimensional space, and when I multiply I'm getting r, and this also represents another transformation. So what you're doing is that when you're multiplying, a transformation is happening, a transformation of a lot of things are happening. Let me show you how this space looks like. Okay, so if a becomes 1 comma 2 and 3 comma 4, right? 3 comma 4. So this is how the space looks like. The original xy, this is my original xy, and this is the transformed space. So this matrix is representing this space. I hope you got the point. I hope, like, from, and let me tell you this, where did the concept of matrix came from? The matrix idea of matrix came from linear transformation only. Before linear transformation, we did not have any matrix. Okay, so for linear transformations, we have introduced a concept called as matrix. And what matrix stores? Matrix stores a given set of vectors. Let's say I'm writing A is equals to 1, 2, 3, 4, 5, 6, 7, 8, 9. What it represents? It represents a three-dimensional space which has three vectors v1, v2, v3. v1, v2, v3. Right? This is v1, this is v2, this is v3. And what are this? These are unit vectors in itself, right? If you take transformation, these are unit vectors. I can show you, but I don't think so. Like, let me search. Three-dimensional linear transformation. Let's search transformation visualization. Let me see if there are any. No, I don't think so. 3D matrix visualizer. So this is what a space looks like. But I hope you have understood, right? Anyways, we don't have to come here. This is the meaning of a linear transformation and matrix multiplication. Now, here comes the most important part, which is determinant. I hope you have understood that what we are doing in matrix multiplication is we are taking one transformation, another transformation, multiplying it with both, and we are getting a totally new space. And that new space belongs in the given dimension. Sometimes it might expand depending on the matrix. If it is a square matrix, then most of the cases it will remain in the same direction. If it is a rectangular matrix, then I will go into another dimension. For example, let me show you this, what to tell you. Let's say I have a matrix. Like I have two inputs, right? Let's say I have a matrix. I think I have non-square matrix. I'll go there, but I hope you have understood that what is the meaning of linear transformation and matrix multiplication. Now let's talk about determinant. Determinant is also the very wrongly interpreted concept in mathematics in our school days. We have taught that, let's say I have a matrix A, B, C, D, then the determinant of this would be, we represent determinant with this, I believe, right? Determinant of A or determinant of A, somewhat like this. Now, it will be AD minus CD, and whatever you get, that is the determinant. But what is the meaning of it? Why, like, how can we visualize a determinant? For example, let's say I am transforming my space by 2 units. I'm changing the I unit by 2 comma 0 and Y unit by 2 comma 3. Okay, now, before we go to this transformation, let me come back to my standard two-dimensional plane. So in standard two-dimensional space, this is my I cap and this is my J cap. Okay, and whatever the area I get, whatever the square area I get, right, this is determinant. Simple. And if I represent this matrix would be 1 comma 0 and 0 comma 1. And if you take determinant of A would be 1 multiplied by 1, 0 multiplied by 0, 1 minus 0, it will be 1. So whatever the square area I'm getting here, that thing is known as determinant. Okay, here for this matrix, the space is x is expanding by 2 and y is expanding by 3. It means that my determinant would be 6. Okay, what does this represent? Let me come back here and I'm putting uh, 2 comma 0 and 0 comma 3, right? 0 comma 3. Now you will see that if you take this square, right, for this transformed space, this will be equals to 6. This is what determinant represents. Determinant represents that how a given block has changed with respect to the original space. That is the definition of determinant. Okay, for example, if I make this vector as a is equals to 2 comma 0 and 1 by 3, then because of this thing, the x might get expand. The x might expand. 1 unit will become 2 unit. But because of this vector, the space might be tilted and stretched or compressed. So let's see what will happen. So here I'm writing 1 comma 3. So you will see that the space has rotated, tilted a bit, and now the whatever the square you are getting, actually if you see, it is not a square, it has become a parallelogram or a parallel. uh, it might become a parallelogram, or if you're talking about three-dimensional space, right, then in that case we will have a cube, and based on how much you expand the space, how much you contract or rotate the space, the resultant square you will get, right? We call this as parallelopiped. And let me tell you this, that if you are going for masters in computer science, AI field specifically, or if you are going in masters in mathematics, right, then you might see integration in linear algebra. Why is it? Because, sorry about it, so sorry about it, but because the reason is that here, sometimes diagram might get skewed a lot. It might compress, it might expand a lot, and sometimes you'll not even get a definite shape. Just see what is this, or else let me put it a negative value, minus 5. Just see the space. Now tell me, how can you calculate the area? How can you calculate the determinant? Yeah, if you have matrix, you can easily calculate, right? With this matrix, I can easily calculate determinant. But if I go from geometry, how can I solve? What we will do is that we go through integration. We try to calculate the given space, this space. From the concept of integration, we try to put small squares, and by filling small squares, we try to cover the entire space, and the entire space area will be equals to the total number of squares which has been filled to get the entire area of this figure. Okay, so this is how we like try to combine two principles, linear algebra and integration. Okay, anyways, let's go back. I hope you have understood the definition and the thinking of determinants. Now the next concept is inverses. Okay, so inverses are Very important, and I have talked about inverses a lot, but I'm going to talk about inverses from geometry perspective. So here I have a vector. I have inserted that vector. That vector can be anything, x, y, and zf, whatever. The vector can be anything. I have inserted that in a given function, and because of this transformation, because of this function, I got some. The vector has changed. Let's say I got v dash, and the space has also changed. Okay. Now, the definition of inverse is the opposite path. Okay, so there will be another function g dash, or you can say g of x, and when if I put this vector, if I put the vector v dash inside uh, g of x, then I will go back to my vector v and I will go back to my standard space. This is the definition of an inverse, and let me write you here that if f of x is a function which is responsible for this linear transformation, then there will be a function f dash of x which will be the responsible for the undoing of the space. Let's say I have taken my space and I have transformed so hardly on that space, and I did not like this transformed two-dimensional space. Now I want to go back to my original space. Then what I will do is that I'll just call f dash of x and it will act as an undo button. It will go back to my original standard space. Okay, now, I have told you, right, that um, they are some special cases, and because of that special cases, what happens is that let's say, let's say I have a two-dimensional vector. Two-dimensional vector. I have passed that in a function, and what this function is doing is that because of this function, I went into one-dimensional space. So what happened is that I was in my one-dimensional space. When I entered the function, when I called the function, because of that function, I have entered into a transformation where two-dimensional space has become a single-dimensional space. Then my vector will lose. Let's say I have some I cap and j cap, right? So my vector will lose any of this. So in the transformation, as a result of this transformation, I will be remained with either I or either j. And if this case happens, if any of the dimensions reduces, then there will be a information loss. You might lose I, you might lose j. And because of this, if you reach this condition where dimensionality reduction is happening, then for this particular case, there will be no f dash of x. It means it will not have a inverse. And why is it happening? There is a rule, right? If you remember, the rule tells that if you input some x value, then function should have only one single output at a given time. This is one of the definition on which the functions has been built. If you remember in 11th class, we have studied one-to-one injection and one-to-many and different things, right? So here, you can map, right? One input, I can't exactly recall the function property name, but it tells that if you give one input, you cannot have multiple outputs at the one side. It can't point to multiple things at a given point. But here, if you try to insert something inside of f of x, then it will point to different answers, and you will end up having infinite answers. Infinite answers. For example, let's say you are having I comma j. I want you to read about this. Read about what will happen if dimensionality reductions happen and why they are no inverses when a linear transformation goes through dimensionality reduction. Okay, so anyways, let's say I had two dimension, and just imagine that you are having only x, and this function is having f of x comma y, and you are trying to go from one dimension to two dimension at once. Then what happens is that you might map I, but you like your function will not have the capacity to point j, right? It will never figure out what is this j, because that function, that whatever you have implemented, right, whatever the function you have, right, it don't have the capability, it doesn't have the power to map another dimension. It is a inbuilt nature problem. Okay, so this is what happens if dimensionality reduction happens, then there will be no inverses. So another definition, that if someone asks you that like tell me when a given matrix will not have an inverse, tell them that if dimensionality reduction happens for that matrix, then it will not have a inverse, right? If I'm coming from 3D to 2D, no. 2D to 1D, no. 1D to 0D, no. No inverses will be there. For example, I can take another scenario. Let's say I'm going from 2D to 3D. Then in that case, will it have inverses? Might be, but I'm not sure. Like in that case, if I'm drawing another case, that if I'm going from 2D space, because of this function, I'm going to my 3D space, then in this we can't exactly tell what is the inverse, but we try to do something called a pseudo inverse, so it will have a pseudo inverse. Okay, okay, so to understand this pseudo inverse, we have to come back to, where is my, yep, non-square matrices. This is one of the important concepts. Okay, so I hope you are getting, like as we move along, that let's say I have a square matrix, right? Most of the square matrix, whatever the operation you do, whatever the transformation you do, if it is a 2D matrix, you will remain in 2D if it is a square. But rectangular matrix, non-square matrix are sort of different. Why is it different? Let me tell you that here I have, let's say, 2, 3, 4, 5, 6, 7. So if you see here, I have I, J, K, but I have only two rows. So what this tells us is that you will have f of, I'm getting a bit confused here, but I'm not sure. But what happens is that the columns represents the number of dimensions, and rows represents the number of dimensions that you will enter after transformation. So if you try to do like transformation of this matrix, linear transformation, then this is a 3D matrix, but you will end up in 2D space. Okay, for example, if it has 2, 3, 4, 5, 6, 7, then you can see there are three values. It means that it has two dimensions because of ij, but because of three rows, what you will do is that you will end up from 3D to 2D. Like this, you can swap. Let me fix this in your head, that rectangular matrix acts as a, what's the correct word, as a like instrument to go from one dimension to another dimension. If you want to jump from 2D to 3D, or 3D to 1D, or 3D to 2D, whatever dimension it might be, or 10D, right, 10 dimensions, you can do that using rectangular matrix easily. Okay, so I'll share the notes. They are like mathematical description which I have learned before coming to this class. But yeah, yeah. So this is about it. And uh, the last concept is dot product and cross product. Okay, so let's quickly talk about dot product. Let's say I have a vector v and vector w, right? So let me draw w something like this. Okay, so here dot product is basically, if I put projection on this vector, right? Projection of projection of W on V, right? Whatever the resultant vector I get, that is known as a dot product. And because if you take two vectors are parallel, let's say this is V and this is my W, then the resultant vector will be V, or resultant vector will be the vector which has the highest magnitude, because two vectors are parallel, and if you draw projection of W, then W perfectly aligns with V. Okay, so this is about it. Now if vectors are perpendicular, let's say this is my vector V and perfectly perpendicular to it I'm taking W, then you can see that if I draw projections, it will never fall on V. And because of this, if V and W are perpendicular, then the dot product of these two will give me 0. Okay, this is the definition of a dot product. This is how we visualize dot product. Now cross product, talking about cross product. So let's say I'm having a vector V and vector W. Okay, so the definition of V and W is that when I write V cross W, then what I'm trying to do is that I'll take this vector V, move it, move it, and put it on top of V. Similarly, take vector W, move it on top and put it on W. And whatever the area which get occupied, this area is known as V cross W. Okay, and you can practice numericals and all after that. Now let's come back to the main concept, which is eigenvalues and eigenvectors, and we will enter into the core, into the math as well after intuition. So let's talk about eigenvalues and eigenvectors now. First, eigenvectors. Till now, I hope you are very much clear with all these concepts. If you are clear, please give me a thumbs up. Okay, so I hope you are clear with all these concepts. Let me draw a perfect circle. Yep. Okay, now we are entering into eigenvectors. I know very long 50 minutes introduction for this concept, but it is important to understand this. Okay, now what is an eigenvector? To explain you this, we need to go back to this linear transformation. Okay, nice. Let's come back to my two-dimensional space. Okay, this is my two-dimensional space y and x, and standard space. Nothing is changed. Okay, now just imagine that I have my vector v. You have your vector v, and what I will do is that I will put a straight line here. Straight line. I'll tell you why I'm putting a straight line. Straight line. Okay, both directions. On both directions, I have put straight line. Now, what I did some transformation. I have put a function, and this function has altered this two-dimensional space. Okay, and the two-dimensional space has been changed. Just imagine that because of this, I got a space something like this, right? This has my, let me draw from this. This is my y dash, and this is my x dash. I'm just drawing, right? This, let's assume that this is my transformed space. I know very bad diagrams and all, but the main thing I want you to observe here is observe my pretty beautiful vector v, right? Even after linear transformation, if a vector has not changed its original vector, original direction, the given vector is an eigenvector. Is an eigenvector. So I hope you have understood the definition and imagination as well. I hope you are able to visualize it, that I did some transformation, and the vector which I had before, is not the same. Let me tell you, it's not the same vector. It might squash, it might expand, right? It might like expand, but like the original vector, it might expand or it might squeeze, right? But the direction will be the same. Whatever the line I had, right? Let's say this is my line 1, right? Whatever the line I have, it remained on that line even after the transformation of f of x. That thing is known as eigenvector. And let's assume that after this transformation, my vector v has changed to half. Let's assume that like 1 by 2 has been happened to my vector as a result of transformation. Then the squashing or diminishing which happened, expanding or squeezing happened, right? The amount it has expanded or the amount it has changed is known as a eigenvalue, and it is represented by lambda. I hope you have understood that what is a eigenvector. Here v is a eigenvector because it has not changed its direction even after transformation. Yeah, it might have been stretched or it might have been compressed, but it never changed its direction. Okay, so that vector v in our case is a eigenvector. Now, the amount it has been squeezed or the amount it has been compressed or expanded, right? That thing is known as eigenvalue and it is represented by lambda. I hope you have understood the intuition, the definition of everything before we go into math, because math might be a bit tricky and I wanted to go into a differential part, but we will go back to this topic after we complete calculus. Okay, so just we will see bacha mathematics. Okay, so here let's try to draw mathematical expressions from the definition. So can I write that, let's say my transformation is A, and what I did is I did transformation on V, and even after I did it, my vector has been the same. So it might have expanded or squashed by lambda V. So this equation is known as equation for eigenvectors. Till now, very clear? Very clear? Thumbs up. Okay. Now. If you observe, A, what is A? A is a, can I say A is a matrix? What is V? V is a vector, but it is also a matrix because matrix is nothing but set of vectors. So this is also a matrix. What is lambda? Lambda is not a matrix, it is a number. And this is also a matrix, this is a vector. Now if you observe, what you're trying to do is you're trying to compare a matrix product, matrix multiplication with a scalar product, right? You're multiplying a vector with a scalar and you're comparing it. Like if you see, this equation is not complete because it's like you're comparing two different units. Like you're saying that, okay, this earpods and this pen, I'm trying to compare it. These are two different things, you cannot compare them. Here on the right hand side you have scalar thing, you are like basically expanding a vector, and on the right hand you are getting a matrix. How can you compare a line with a transformation, with a matrix? You can't, right? So what we do is that we try to complete this equation. Okay, so we'll multiply I on both sides, and if I multiply with I, nothing will change on the left side. But here, lambda I and V. Okay, now if I take this back here, if I take this back on left side, A V vector minus lambda I V will be 0, right? And if I take my vector common, then A minus lambda I V is equals to 0, right? I'm just telling you that how we can find a eigenvector and how we can find the eigenvalues as well. So here, we need is that what we need to understand here is that this thing, right, A minus lambda I will give me a matrix, right? And what did I tell you? What is a matrix? What is a matrix? What is a matrix? Matrix is a linear transformation. And if you observe the linear transformation of this matrix, let's say I'm calling this matrix as Z. So if you take Z, Z is representing a very, very special matrix, right? It is representing a very, very special transformation. And you know what is this transformation? This represents dimensional loss. And what did I told you? That if dimension loss happens, then what happens? Let's say I have a 2D figure. I will get squashed to 1D, dimension reduction. And you tell me that if there is the entire lines has collapsed, let's say like I have this lines, X and Y lines. If there is a square, perfect square there, you can calculate the area. But it has become a single line, then what is the area of it? What is the area of this square? A line. 0. A line will not have area. We know that, right? So if you calculate the determinant of A minus lambda I, it will give you 0. Okay, so after getting from this thing, you will get lambda. And let me tell you this. If A has n cross n numbers, then lambda will be n values. If A is equals to only one dimension, then you will get lambda as a single value. If A is equals to 2, then you will get lambda as two values, lambda 1 and lambda 2. If there are n numbers in A, then you will get n lambdas. Okay, so what you will do is that you will take the value of lambda, put it here, and you will get a equation, right? You will get a value as like you will get a matrix here. You will get a matrix after putting value. This is our matrix Z, right? So Z and V are two matrices, basic terms, right? And it is equals to 0. Can I write that? Let's say this is A, B, C, D, and this is X, Y. I'm just taking random values, is equals to 0. And how can we solve this? Do we know how to solve this? Do we know how to solve this? Can I write this thing as A, B is equals to 0? And we know how to solve this through Gaussian elimination. We studied in class 1 Gaussian elimination. So this is how we calculate the vector V. Okay, got it. Now here's the thing. What did we understood from this entire math? We understood that whatever the transformation there is, right, there is probability that irrespective of the transformation, there will be one vector which will not change its direction. And that vector is going to be the most important vectors. And I will tell you why it is in 1 minute. But before that, I want you to tell me, are you very clear with what is eigenvector, eigenvalues, its definition, mathematical derivation, and everything? Okay. Okay, now till now we have understood. Where is my, yep, okay. Till now we have understood linear algebra, combinations, transformations, multiplication, determinants, inverses, non-square matrices, dot and cross product, eigenvectors and eigenvalues. Now enough theory. I don't want this to be a lot of theory and every time. So let's talk about one practical application, which is principal component analysis. Okay, so this is one method which we use in data science, in machine learning a lot to visualize higher dimension data in simple format. So let's talk about principal component analysis now, a new topic for us, very new. And this is the implementation part as well. So let me draw here, let me write here, principal component analysis. Okay, and this is also known as PCA. Uh, Give me a thumbs up if you already know about this topic. Give me a thumbs down or something like reaction, that some other reaction if you don't know about this topic. Because if you know, then I will not go into the reps. If you already know, then if you don't know, then I will try to explain. I'll not take much time, but I'll try to explain what it is. So okay, ठीक है, sure, ठीक है. So let's take an example. Let's take an example that. hmm, Okay, I think I have read this in a book of, I'll share you the book. Let's say I have, what's a practical example which I can give that you can also understand. Let's say I have cats, right? Cat 1, cat 2, and cat 3. Okay, and for each cat, I have calculated their genes, their different genes, right? Here, let's say I'm writing gene 1, gene 2, and gene 3. Okay, now I'm writing some random values 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so um, for cat 1, it has three different genes in its body, and the value of genes are 2, 5, 8. For cat 2, it has also three different genes, and the values are 3, 6, 9. And cat 3, 4, 7, 10. Okay, now my question is, I need to understand this given data in a very in detail level, right? I want to understand this in detail. I want to understand what is this pattern, what this pattern is telling me, and I'm trying to draw some conclusion. That is my main question. Okay, so how I can do? Just imagine that. Okay, so I hope you have understood the table, right? This table represents the different cats and their different genes in them. Now now just imagine that, to visualize the data, I'm making it simple. Okay, so let's say I have cat 1, cat 2, and cat 3. Okay, and I have my gene 1, 2, 3, 4, right? 1, 2, 3, or 2, 3, 4? Yeah, 2, 3, 4. Okay, now tell me how I can visualize this data, this example 2. This is my example 1. We will come back to this example after understanding example 2 and 3. So can I draw this in a number line, and this is my origin 0, and this is my gene number line, and cat 2 is having what number? 2. So cat 2 is lying at 2. Sorry, cat 1 is lying at 2. Cat 2 is lying at 3, and cat 4 is lying at 4. Okay, so if it is a single gene, I can draw a number line, and on top of that I can put the points of different cats, right? Now, now just imagine that I have changed my dimensions. I have changed my dimensions to, let's say I have cat1, another example. I'm taking another example, cat1, cat2, and cat3. Gene1, gene2. I have two genes now. So 2, 3, 4, and 1, 2, 3. I'm taking an example, random example. So I can imagine this with two different axes, right? The axis 1 will represent gene 1, the axis 2 will represent gene 2. Okay, now if I draw 1, 2, 3, 4, 1, 2, 3. Okay, see that the common intersection point, gene 1 of cat 1 is 2. So this and this 2 point intersection is my cat 1. Okay, and similarly this 2 point intersection is my cat1, cat1, cat2, and this 2 point intersection is my cat3. Okay, very simple to understand, very easy to understand. Okay, now let's come back to this thing, this example. So if I draw, just I'm taking smaller values, 1, 1, 1, for example, right? Because I want to draw this in plane. 1, 1, 1. Okay, and 2, 3, 4 is a smaller value. So for first example, I can draw this in a three-dimension format: x-axis, y-axis, and z-axis. G1, G2, and G3. And what I'll do is that what are the common intersection point of these three vectors, 3 points, I'll draw it. Let's say this is my C1, cat1, cat2, and cat3. So I can draw and visualize the points, and I can cluster the cats which are near, the cats which are far, and from that I can tell like why they are far, why they are near. I can like tell that which types of cats have similar genes, which types of cats has different genes, based on this graphical representation. From this single dimension graph, from this two-dimensional graph, from this three-dimensional graph, just imagine that you can see from this graph, you can tell that cat 1 and cat 2, the breeds of two cats are very near, the genes are near when compared to cat 2, because cat 2 is away, right? From this graph, from this I'm trying to I can interpret that, I can tell what is the meaning of that, what is the pattern I have observed. Okay, now my question is, let's take another example, c1, c2, c3, and I have gene 1, gene 2, gene 20. Now tell me, so for single dimension, you drew a number line, we have understood. For when genes are two, you drew a XY and you have understood. For gene 1, gene 2, gene 3, you do XYZ and you have understood. Now when you have 20, it means you have to draw a space where it has 20 dimensions. So please go ahead and do that. And I can guarantee you that if you draw a 20-dimensional space, you will understand the pattern. But how? How can you draw 20 dimension patterns at once? You can't. Human brain can't. We can't even draw 4-dimensional space. So here where PCA comes in. Principal component analysis. I always forget the name, but principal component analysis tells that even though you have n dimensions, right? Even though you have n dimensions, principal component analysis helps you in extracting the patterns from this hundreds of dimensions, from this n dimensions. This is what PCA do, right? This is why we use PCA. Okay, now what happens in PCA? What exactly we do? To understand what we do in PCA, let's take a simple example. Let's take example of two dimension, right? Uh, cat 1 and cat 2. Cat 1, cat 2, cat 3, cat 4, cat 5. Okay, gene 1, gene 2. Now, what I will do is that first of all, I will draw a line. I will draw my gene 1, my gene 2, Okay, and I will draw the points as well. Let's say this is my cat1, cat2, cat3, cat4, and cat5. Okay, now cat5. Okay, 1, 2, 3, 4, and 5. Now I have a points, right? I have taken a two-dimensional plane. I have plotted points on top of that, right? I know cat1, cat2, cat3, and all. Okay, now what we do in PCA? In PCA, first we draw the given lines like this. After that, we draw a line which goes from origin. Okay, let me draw this line with different pen because it is really important to understand. Okay, so I'll draw a line from origin. Okay, now understand this. What I'll do is that I will draw a random line, a very random line, something like that. Okay, and after drawing that line, I will do something. What I will do, to understand what I will do, you need to understand from one point. So I'll take one point as example. Okay, so let's say this is my line which I have drawn, and this is my one point. Let's say cat 1 point. Now I will draw projection from this point and I will take this thing. Okay, so I know this point. If I know this point, then I can tell the distance from origin to this, right? So let's say the distance is C. And when I draw projection of this line on top of this, but from point 1 to this line, then I will create a rectangular, right angle, not rectangular, right angle. Now, if I say that this distance is A, this distance is B, no, let's say that this distance is C, B, and A. Okay, now can I write that from Pythagoras theorem, the hypotenuse will lie opposite to right angle triangle. So here, this C is my hypotenuse. So can I write from Pythagoras theorem, A square plus B square is equals to C square? We can write it. Now, from this, I can extract A square. A square is equals to C square minus B square, and I'll take only A square. I'll tell you why, but understand this. Okay, so when I draw projection from the concept of geometry we have studied, I can exactly tell how much length it will be, right? And I can tell on what point this projection will fall. Okay, and how I can tell from the concepts which we have studied in two-dimensional geometry. In 11th class or 12th class, we have studied something called as circles and all. From that, you can exactly tell the projection point of intersection. Okay, now why I'm telling you this? Because what we do is that we draw projections. We draw projections of from this point onto the line, Okay, after drawing projections, what we will do is that we take the distances. Let's say this is my distance 1, distance 2, right? Distance 3. This is my distance 2, distance 3, right? We'll calculate all the distances 5 and 4. So what we'll do is that we first of all draw a random line which aligns towards, let's say, y-axis, for example, y-axis, right? I'll calculate all the distances from the origin to the projected point, right? So I'll calculate D1, I'll calculate D2, D3, D4, and D5, right? And these points can be negative. So what I'll do is that I'll take the squares as well. So I'll calculate D1 square, D2 square, and D3 square, D4 square, D5 square. And what I'll do is that I add all of them. Sum of squares of distances. Okay, I'll add them, I'll put it aside. Let's say I'm putting in an array, right? I'm putting in an array. So I'll put this value, whatever value I get. Now, after this, what I will do is that I'll take the line which I have, I will tilt it and tilt it. After tilting it, again I will calculate the distances. I'll calculate the projected distances from the origin. Same process, right? But the only thing is tilted. Now, after tilting it, you know, I'll get some other distances. Again, this is my 10-1, 10-2. In 10-2 also, I'll do the same thing. I'll store that in array. 10-3, I'll store the same thing. I'll do it again. Now, like you might ask, like Jabir, don't you think it will add so many operations, right? By tilting it every angle, 1 degree, 1 degree. It will, like, we have to do all the entire three-dimensional space to calculate all the distances, right? So the goal why we are tilting it is that after getting all the values, what we'll do is that we take the maximum value. Okay, we take the maximum value, and that will be our line. That will be our principal component analysis line 1. And I will tell you what is that line in few minutes, but that is the goal, right? Keep on tilting it, and keep on calculate the maximum value. And the moment you get the maximum value, the sum of squares of all distance, the maximum value which you get, that line will become your PC1 line. Okay, okay, got it. Now, here's the thing that is there a method, is there a logic which we can tell instead of doing this many tills, can I tell, or is there any logic which I can use in order to reduce the operations? The logic is that if you take this diagram, so this diagram looks something like this. Now tell me, this is fixed. This distance is always fixed. C will not change. The only change is A and B. And I can write C square is equals to A square plus B square. And what do I want? I want this A to be maximum. If I want A to be maximum, then B has to be very minimum. Are you getting me? That if I tilt this very towards to like very close to the point, then the length of projection here will be very, very small when compared to the distance of the line from the origin, right? This will be very big if this is something like this. So the goal is that instead of calculating every other thing, do one thing. You know SPD, right? I can't remember the full form of like a singular vector machine, support vector machines, my bad. Support vector machines. What it tells you, that draw a line which is near to the points. So do the same, right? We will draw, let's say these are my points, point 1, point 2, point 3, point 4, point 5. We'll draw a line in such a way that it is very close to all the points such that its projection is very small and length is the maximum length. The length you will get is the maximum length. And you know what is this line? This line we call it as PC1. And if you observe this line, whatever the vectors you draw, it is eigenvector. It is a eigenvector line. Okay, so what we will do is that just assume that you got this line and you know the points, right? You know this point, and all. If you know 2 points in the given line, then you can calculate the slope, right? Slope, let's say the slope is 0.25. If the slope is 0.25, then the x is 4, y is 1, right? It means that for every point on the PC1 line, there are 4 genes 1 and gene 2 is 1. It means that the characteristic of points of gene 2 is more than gene 1. Okay, maybe hard to understand, but yeah. Now, let me tell you this. Okay, not yet completed. PC, what's the full form? I forget. Principal component analysis is not completed. Now you have calculated these points. So let me draw this here. This is my line. Points are close, right? Points are close. Yeah, something like this. This is my PC1. Now what I will do is that I'll draw perpendicular line to this PC2. Okay, and I will rotate this line now. I'll rotate this PC1 and PC2, right? PC1 and PC2. And before rotation, I will calculate the eigenvalue, right? Eigenvalue of PC1. What is the formula? There is a formula that sum of squares of distances, all the distances, basically the sum of this thing, the thing which you did. Take that divided by n minus 1, the total number of points divided by n minus 1. So this thing will give you a eigenvalue. Let's assume that the eigenvalue is 0.8. Okay, and PC2 line, let's say PC2 line, we'll do the same thing. We'll draw projections on top of it and take the points. So again, for it also, sum of squares of distance for PC2 line uh, divided by n minus 1. Let's say it is 0.2. It might not be always 1. I have taken an example. So PC1 has eigenvalue as 0.8 and PC2 has value of 0.2. Okay, so and we'll draw points will remain the same. Points will remain as it is, right? 1 point here, 1 point here. Now, what it tells you is that PC1 has more gene characteristics. The cats is tends to having the gene 1 characteristics than gene 2. So PC2 represents the lower boundary, the lower cluster, the small cluster of cats, and PC1 represents the big cluster of cats. Like this, we calculate PC1 and PC2, and this is known as principal component analysis. Okay, now there is one more thing that we have taken 2 dimensions and we have tried to understand the concept. If you take 3D will also be the same, but the only changes you will get 3 lines: PC1, PC2, PC3. If you take 4 lines, then you'll get 4 lines and you need to understand that PC1 and PC2 has to be perpendicular to one another. Right, it is the given rule. It has to be perpendicular. If you take 3 dimension, then P1, P2 and P3 should be perpendicular. It will be something like this, and the angle will be 90 90 90 with one another. PC1, PC2 and PC3. Okay, 90 90 90. Now if you take 4 dimensions, then it means, just try to imagine it, that you will get 4 lines and 4 lines are perpendicular to one another. It means that you are in 4 dimensions and 4 dimensions are perpendicular to one another. It's crazy, right? It's crazy. And if you try to solve 4 dimension, then papers will come, like you will be solving papers and papers. That is why whenever we do principal component analysis, we give it to computers. We give this data, it will give the results in a tabular format, and there is, like, you can solve it. There is something called as component variance, which again comes in integration, right? So we'll see, this will come back to eigenvectors and this concept again after studying calculus. So yeah, this is pretty much it. This is the overall concept, and moving forward, what else do we have here? Yeah, so we have studied eigenvalues and PageRank, right? Let me tell you this. Whenever I'm searching something, I have taken visualization as well. This is how you can see here. I have how many dimensions? Let me go. You can see like how many dimensions are there. 13 dimensions are there. So this is a 13 dimension PCA analysis. This is how it looks like. Anyways, for to understand what exactly happening, we need to see a bit of calculus. We'll come back to it, don't worry. So the next topic is page rank explanation. So I don't want to go into the depths of it, but let me tell you that initially when Larry Page and Cyan, who's the another guy, Cyan Berge, something like that. I can't exactly remember the name. When Larry Page created Google, the formula which happened to rank pages is the formula which came from eigenvectors. Okay, and there is something called as eigenfaces. Eigenfaces is a concept which you can, like, let me show you eigenfaces. Eigenfaces are recognition techniques that uses PCA to reduce high dimensional data of images into smaller units. It means that you can have tons of similar matching images in a single place with very less storage, and this is how it stores it. So you can detect the people faces by just giving some small data. So what happens is that, let me just show you. So by just giving one small detail, you can extract the entire face of a person. This is known as eigenfaces. And this concept is related to eigenvectors only. From eigenvectors only, we get eigenfaces and all. So I don't want to go, like, we'll see in next class if needed, page rank explanation and eigenfaces explanation, because again it will go up to 2 hours. Like, I don't want to do that. What's the time? One. So let's stop it. We'll cover some other time. So if you have understood all these concepts, then thank you so much. It really means to me a lot. So yeah, thank you everyone. Thank you for watching this entire 1.5 1 hour 40 minutes lecture. It was a long one, I know that, because if you see our previous lecture, it was 40 minutes, 50 minutes at max. I was trying to make 1 hour, but I made this lecture 6 with, like, it is around a length of 1 hour 40 minutes. I wanted to make it more because I want to cover more topics and practical concepts as well. I wanted to discuss practical concepts. So I have cropped the, short things and all, but I hope you have learned what is eigenvectors and eigenvalues, and you have seen, I hope you have understood the implementation as well, the practical implementation of why do we use it and why do we use it there. So with that being said, there is one more last lecture of linear algebra. After completing that, we will go to calculus and probability. So thank you for watching. It really means to me a lot. If you have any doubts, please to DM me personally or comment down. I'll be more than happy to clarify your doubts or anything as such. So with that being said, I'll see you in the next one. Bye.